The last air conditioning process that we're going to take a look at is that of an evaporative cooler. Now these are systems that you would not want to use in a humid climate. Sometimes they're called swamp coolers. I lived in New Mexico, Albuquerque, for a number of years, and there that was the way that they actually cooled and provided air conditioning. It's so dry that you can use these evaporative coolers, and you mainly use them throughout the summer. But essentially what happens is air is drawn through a system that adds humidity, and through the process, the air going through the phase change, or sorry, the water going through a phase change, it evaporates. Excuse me. And what it does is it cools the airstream, but you're increasing the relative humidity of the air in the process. So it is a humidification and a cooling process occurring at the same time. And that's why if you live in a climate that is humid, you never would want to really do this, because it's just going to make it even more unbearable. But it works fine if you live in the desert, like in New Mexico, Arizona, places like that. So what we'll do, we'll begin state 1. And then we have our exit state over here, state 2. And all we are doing is we're adding moisture. And there are different ways of adding this moisture. You can pass the air through a system that is almost like a sponge that is wet. And that would be one way that you can do it. But essentially you have to pass the air through something that will add moisture to the airstream. And as that water vapor evaporates, it cools, and consequently that's what provides the system. Similar if you're outside and it's raining and it's a dry climate, sometimes the rain can cool things off, and that's what it's doing. The evaporation of the water actually causes the atmosphere to get cooler. And so we're relying on a very similar process here. Now, we also have to account for mass flow rate of water coming in. And in order to solve this process, what we do is we usually we have to assume something about the water coming in. And so for that, what we do is we assume the temperature of the water coming in is equal to the temperature of the fluid stream leaving at T2. And the other thing that we need to do for this process, we need to make an approximation about the enthalpy. And for that, we usually assume that enthalpy at state 1 is similar to enthalpy at state 2. So if we were to look at this on our psychrometric chart, I'll just sketch that out here. So there's our psychrometric chart. We have our dry bulb temperature here, specific humidity there. If you recall from the chart that I showed you on an earlier lecture, the enthalpy lines run up and to the left, and consequently, if we're talking a constant enthalpy process, we would be going from state 1, and I'll draw it green because that was the color that I used in my psychrometric chart. But it would go kind of like this, and that would take us up to state 2. So that would be what the process would look like for one of these evaporative coolers or swamp coolers. And then again, what you do is you go through and you do your air balance, you do your water balance, and you can apply the first law, but you calculate it using enthalpy in the way that I've shown you here. So that is the evaporative cooler. What we are going to do next, that will conclude this lecture, but in the next lecture what I'm going to do is work 2 example problems. The first one will be for a situation whereby we are not able to use a psychrometric chart, and consequently we have to use the equations for that. So that's the case where we're not at 1 atmospheric pressure. And then the second example, we will revisit the psychrometric chart, and you'll see how easy it is to solve the problems when you're using the psychrometric chart. So those are different air conditioning processes that exist, and there are many more. There are different combinations of these, but essentially they're all kind of the same thing, and once you get the hang of it, you can figure out how to solve other ones. So that will conclude this lecture. Thank you for your time.